course in industrial design, affine combinations and affine transformations. Affine combinations. Any three collinear points, A, B, and P, can be written as what it is known as an affine combination. That means any of the 3 points can be written in terms of the other two. For example, P is an affine combination of the points A and B if P can be written as alpha times A plus beta times B, with alpha plus beta equals 1. When alpha and beta are positive, then the point P is said to be a barycentric combination of the points A and B. In affine combinations, the coefficients alpha or beta need not to be positive. When alpha and beta are both positive, we say that P, which is a barycentric combination of A and B, divides the segment AB, the segment from A to B, in the ratio beta over alpha. Beta is the number obtained dividing the length of the segment AP by the length of the segment AB, and alpha is the number obtained dividing the length of the segment PB by the length of the segment AB. If instead of the segment AB we consider the segment BA, then we would say the point P divides the segment BA in ratio alpha over beta. As we said before, in general, alpha or beta could be negative. We are going to see what it means for these scalars to be negative. On the screen, it can be seen a point P which is an affine combination of the points A and B, with coefficients alpha and beta. In this case, alpha and beta are equal to 1/2. They add up to 1. Then the ratio beta over alpha is 1. When we move P, now alpha is bigger, beta is smaller than 1/2, they still add up to 1, and now the ratio has changed, still a positive number smaller than 1. If we make alpha even bigger than 1, now beta has to be negative because they add up to 1. This ratio, because beta is negative and alpha is positive, is a negative number. This negative number is bigger than -1. That means that the point P is farther from B than A is from B. If we move P to the other side of the segment AB, in this case beta is a number bigger than 1 and alpha is negative, they still add up to 1, and this ratio again is a negative number. It's a negative number smaller than -1. This means that the point P is outside the segment AB, and in this case P is farther from A than B is from A. For simplicity, and whenever we have this expression here, even when alpha or beta are negative, we are going to say that P divides the segment AB in ratio beta over alpha, in spite that P does no longer lies on the segment AB when alpha or beta are negative. If P is an affine combination of points A and B and Q is an affine combination of points C and D with the same coefficients, then Q divides the segment CD in the same ratio as P divides the segment AB. And this is also true even when alpha or beta are negative. Affine transformations. Affine transformations are mappings from the plane to the plane or from space to space that preserve affine combinations of points. That is, if T is an affine transformation and P is an affine combination of points A and B with coefficients alpha and beta, then the image of P is an affine combination of points TA, TB with the same coefficients alpha and beta. On the left of the screen, we see a polygon and 3 points on the polygon, which are collinear, the points A, B, and P. That means P is an affine combination of points A and B, with coefficients alpha and beta. P is alpha times A plus beta times B, with alpha negative and beta positive. We make a copy of this polygon and its points, and we get this polygon here on the right of the screen. Now, the transformation T is the identity. The point TA is A, the point TB is B, and the point TP is P. So, of course, TP is in the same affine combination of TA and TB as P is of A and B. But we can change the polygon on the right by making it bigger size. For example, like this. And still, even though the segment TA-TP is of different length than the segment AP, the point TP is in the same affine combination of points TA, TB as P is of points A and B. And this is true even we would change the position of the point P, for example, to this position, or the point B. We can also rotate the figure, and again, TP, TA, and TB are collinear, and TP is the same affine combination of points TA, TB as P is of points A and B. And also, if we translate the figure. But not all the transformations in the plane are affine transformations. Here we have an example of a transformation that is not affine, that maps the little rectangle on the left to this funny figure on the right. The points on the left, A, B, and P, are collinear. That means P is an affine combination of points A and B. Nevertheless, the points on the right, TA, TB, and TP, are not collinear. TP is not an affine combination of TA and TB. This transformation does not preserve affine combinations of points. That means this transformation is not an affine transformation. The basic affine transformations are translations, rotations, homotheties that could be contractions or expansions, shears, and reflections. Any composition of these is also an affine transformation. Here we have an example of a translation that is just moving the figure from its position to a different position that preserves affine combination of points. Also rotations preserve affine combination of points. Homotheties, in this case an expansion, shears, and reflections, which are also called symmetries.